Okay, so for this problem right here, hopefully part A was pretty easy. It's exothermic because enthalpy is negative, right? Releasing energy, so that's exo. Part B is just thermochem stoic, so we'd start with our two numbers, 20 grams sulfur, 25 grams oxygen, and then we solve for kilojoules. So this is what we did last time. Any questions on the actual solving?
No.
Okay. This is where things can get a little tricky though, because we are going to look for the limiting reagent, and we always say the limiting reagent is the compound that makes a smaller number, right? Now, this one's a little bit complicated because there's a negative sign. So technically, numerically, what's the smaller number?
It would be oxygen.
Yeah, numerically 231 is smaller, right? And so it might be really easy to say, oh, oxygen is our limiting reagent. However, let's talk about what the negative sign means. The negative sign means released, right? So 185 kilojoules are released if we run the reaction with sulfur, and 231.25 kilojoules are released if we start with O2. Okay, makes sense? That's what the negative sign means. So if we look at it from this perspective, which compound makes less energy? Yes, sulfur makes less energy, and so the limiting reagent here is actually going to be sulfur. Okay, so the amount of energy that is released is going to be 185. So that's kind of the part we didn't talk about. When we are looking at limiting reagent type problems with thermochem stoic, we always look at the magnitude of the energy, not the numerical value. Okay, because the sign, the positive negative, just tells you which way the energy is going, not so much how much energy is made. Alrighty, guys. So we're gonna do stoic, regular stoic for this. We take our limiting reagent, which is sulfur. So 20 grams sulfur. You find the molar mass, 32. You set up the mole ratio. It's 1 to 1. And then the molar mass of SO2, which is 64, and then you should get 40. Okay. Yeah. Okay, so if we take a look at D, it says, if the synthesis of SO2 gas is spontaneous. Now, let's talk about this word spontaneous before we move on. So I want you guys to write this in your notes. We're going to talk a lot about this in unit 13, 12, or 13 in thermodynamics. But spontaneous basically means the reaction, it wants to happen. Okay, so wants to happen. The technical term is favorable. Whoa. Favorable. Okay, so this is a reaction that is favorable. It wants to happen. Okay, an easy example of this is, I always talk about bombs with this unit, but like a bomb, right? You add a little spark to it, and then the reaction wants to blow up, right? That's a favorable reaction. And that's kind of what's happening here. You're adding energy. It says when the reactants are heated, it wants to happen. And then the question is asking, is it likely for the reverse reaction to be feasible under ordinary conditions, and explain your answer. Now, what the reverse reaction is basically saying is, if this reaction happens, right, and it releases energy, can we go the other way? Can we make SO2 turn back into S and O2? Is that reaction possible? And the answer is no, because if you think about it with the bomb example, once a bomb goes off, is it really possible to bring all the components and make the bomb back together again? No, it's not. So the answer is going to be no. And the reason why is because this is spontaneous. It's favorable in this direction. Okay, so you would say something along the lines of the reaction is favorable, okay, the way that it is. Okay, now in order to go the other way, we would have to add the amount of energy that was released. So theoretically, if we had a bomb go off, it is theoretically possible to make everything come back together. It would just take a lot more energy. You would have to gather all of the gases and different particles that were released, bring them back together, and then make the chemical reaction go in reverse, which is highly unlikely and not really going to happen. Yeah. Okay, so we are going to move on to something called Hess's law now. Okay, so I want you guys to write down the term Hess's law. And Hess's law is very simple. Hess's law basically tells us if a reaction takes place in multiple steps. Okay, So a lot of times when we have a chemical reaction, it's not just one step. The chemicals don't just go automatically from this to this. Sometimes there are steps that take place in between. And what Hess's law tells us is that if there are steps that take place in between, the enthalpy in whoa, I forgot the H. Okay, the total change in enthalpy is going to equal the enthalpy change of each step. Okay, so if it's step 1 plus step 2, so on and so forth. That's pretty much what it's telling you. Okay, so if a reaction takes multiple steps, the total enthalpy change is equal to the sum of all the enthalpy changes of each step. Okay, so if there are 2 steps to a reaction, so let's say that we have a reaction that takes 2 steps, the total enthalpy change is going to equal the step 1 plus step 2. Okay, that's pretty much it. Now, you guys don't need to know what these steps in between are. They will always be provided for you. But the problems that we're going to do coming up are going to show you the types of Hess's law questions you will see. Okay? But any questions on the general concept? Hopefully it's not too bad. All right, so let's look at 618 now. 618 tells us that you get this data right here. So these are the 2 step reactions. And then it's asking you to find the delta H for this reaction right here. So what we're going to be doing is we're actually going to be organizing these reactions to combine to make this one right here. Okay, so it's pretty simple. It's kind of like a game. So the first thing you want to do is look at the first reaction or the first reactant in the total reaction. You guys see it's CH4, right? So we're going to look for the equation that has CH4. Let's call this 1 and 2. Which reaction has CH4? 1. So what we want to do is we want to make sure that CH4 is on the correct side of the equation. It's on the reactant side. If you look here, this is also on the reactant side. So what we're going to do on your paper, I want you guys to write this reaction because it's set up the proper way. So we're going to write CH4. We're basically just copying down reaction 1. CH4 gas plus 2 O2 makes CO2 gas and 2 H2O gas. Okay, so take a second to copy this down. And then we're going to include the delta H as well. So we didn't do anything to this reaction, so we just copy it down exactly the way it is. All right, so now let's take a look at the second reaction. If you take a look at the second reaction right here, you're going to see that we have 2 H2O gas produces 2 H2O liquid. Now, if we take a look at the reaction that we're trying to make, where is H2O liquid in this final reaction? At the end, the product side, right? So we're just trying to make sure the H2O liquid is on the product side. So what we're going to do is we're going to copy it down because, again, this is set up properly. So we're going to write 2 H2O liquid is made from 2 H2O gas. Okay, so this is our first example, so we're going to keep it pretty easy. We didn't do anything to the reactants or the reactions. All we're doing is copying it down. So what we're going to do now is we're going to combine these 2 reactions to get the delta H for this overall reaction. The way that we're going to do that is we're going to look for a compound that is both on the left side and the right side when you compare these 2 equations. So do you see a compound that's on the left and the right side?
Water.
Water, but specifically what type of water? Gas, yeah, gaseous water. You guys see how there's 2 H2O gas and 2 H2O gas right here. So what they're going to do is if you have something on both sides of the equation, they're going to cancel each other out. Basically what's happening is the 2 H2O that you made here is going to be used to make liquid water. It gets used in the next step. Okay, so they cancel each other out. And then what we're going to do is we're going to look at what is left over. The thing that is left over is CH4 gas and 2 oxygen gases on the reactant side. And on the right side, we have CO2 gas and 2 H2O liquid on the right side. And that's exactly the equation that we're looking for right here. basically what you're trying to do is you're trying to make this equation with these two equations. Okay? This time was really easy. We didn't manipulate it, but the next problems we're going to have to do some manipulating. I'll show you what we have to do when we manipulate. Okay? And then what we do now to find the delta H to solve our problem is you just add up these two values right here. Okay? Now, they are negative, so it's going to be 802 plus 88, and it'll just be the negative 890. Okay, so the delta H, our answer is going to be negative 890. It's just the sum of the steps. All right, so the first thing you want to do is you want to look at your goal reaction, and you're going to look at the first compound in your goal reaction. You got N2O. Okay, let's call these equations 1, 2, and 3. Okay, which equation has N2O? 3. 3 has N2O right here. So what we're going to do is we're going to copy down this reaction. But before we do that, let's take a look at the coefficients. The final reaction, you want 1 N2O, right? But if you look at 3, how many N2Os are there? 2. So what we want to do is we actually want to divide equation 3 in half. So what we're going to do is we're going to divide everything in here by half. So let's copy it down. So N2O, gas. If we divide this by 2, it becomes 1, right? We're going to draw our arrow. N2, if you divide this by half, this also becomes 1. O2, this is 1. If you divide that by half, it becomes 1/2. And then last but not least, the enthalpy, you also need to divide that in half. Okay, now just so that we remember how we did everything, I'm going to just write it. And then I'm going to just write times 1/2. That way we remember everything that we did. All right, so if we want to match the coefficient in the final equation, we have to divide equation 3 by 2. And that's how we get this right here. All right, so far so good? Okay, let's take a look at our next compound. We got NO2. Which reaction has NO2? Yeah, the second one, right? It's right here. Okay, now, what's wrong with the way the second equation is set up?
It has a 2.
It has a 2, so it means we're going to have to divide it by 2, but what else? Yeah, it's on the wrong side, right? You see how this is on the product side? This is on the reactant side. So there are two things wrong with this. First, there's a 2, so we got to divide it by half. The second is that it's on the wrong side. So if something is on the wrong side of the equation, basically what we do is first we just flip the equation. So when we copy it down, let's flip it. So we're going to write 2 NO2, and I know that we got to get rid of the 2, but we'll do that next. But let's just start by flipping it. 2 NO2 produces 2 NO plus O2. Okay, so the first thing you want to do is you want to flip. And then for this one, we just did times 1/2. All right, so we flipped it, and if you ever flip a equation, the thing about the enthalpy is very easy. You just need to flip the sign of the enthalpy. So this was negative 113.1, so we just flip the sign. So it becomes positive 113.1. And we did that because we flipped the equation. All right, now, we said we need to get rid of the 2 in front of NO2. How can we get rid of the 2?
Divide by 2.
Yeah, divide by 2 or multiply by 1/2. And so that's the last thing that we have to do. So that's going to drop the 2 here, drop the 2 here, make this 1/2. And then we got to make sure that we do 1/2. So equation 2, we have to flip it and multiply it by 1/2. All right, and then for the last one, obviously we need to use equation 1 as well. So if you take a look at equation 1, and if you take a look at equation, or the final equation, see how we want NO on the product side. Yeah, what's up? Which one? Second step, what do we need to divide? The delta H? Yeah, I just haven't done the math for it, but I just wrote times 1/2. Yeah, you're good. Yeah, so yes, you do need to do that. I just didn't do it yet. So for the last step, you guys see how there's NO2 on the product side? In equation 1, the only thing that's in the final reaction is NO2, right? So we're going to make sure that NO2 is on the product side. It already is, so let's just copy down exactly what we got. So we got N2 gas plus O2 gas produces 2NO gas. And we didn't do anything to this guy, so we can just copy it down exactly the way it is. Yeah, we do need 3, but yeah, you see it. Yeah. So everything eventually works out at the end. Alright guys, so let's take a look at the 3 equations that we set up. The first one, we didn't do anything to it. The second one, we had to flip and half it. And the third one, we had to half it. So if we take a look, we need to start canceling some things out. So what's one compound you see on both sides of the equation?
O2.
Yeah, O2. So if you take a look at the left side, how many O2s are there?
1.
There's 1, right? There's 1 O2 here. And if you take a look at the right side, there's a half an O2 here and half an O2 here, and that's a total of 1, right? Half plus half is 1. So these guys can all cancel out. Okay, what's another compound that you see on both sides of the equation? N2. You see N2, and you see N2. And there's 1 of each, so they can cancel out. Anything else? Nope, we don't see anything else on both sides. So let's bring down what we have remaining. First chemical that we have is N2O gas. Perfect, that's exactly what we want. Plus NO2 gas, which is what we want as well. That's it for the stuff on the left side. And on the right side, how many NO gases do we have?
3.
3, because 1 plus 3, which is exactly what we wanted. So Hess's law is kind of nice because if you did it wrong, you'll be able to see right away that you did it wrong. Everything will work out at the very end. So if there's something up, that means you messed up somewhere. Alright, so that means we have the correct manipulations for the delta H's. Let me give you guys a minute, see if you can calculate what is the final delta H, and then I'll have you guys try a Hess's law problem on your own, and then we'll move on. Alright guys, so you guys should get delta H positive 155.05. Good with that? So, math-wise, you just need to do negative 163.2 divided by 2, and then you got to do 113.1 divided by 2, and add all 3 of those numbers, and you should get 155. Alright, so first thing we want to do is you want to take a look at NH3. Now you got 4 NH3, so the equation that has NH3 is equation 2, right? But the problem is you got to flip it, and you need to double it to get from 2 to 4. So we're going to flip it first and double it. That's going to give you 4 NH3, and then you draw your arrow. You got to double N2, so 2 N2 plus 6 H2. And so for your delta H, you will have to flip the sign, so it'll be positive 91.8 times 2. And that's equation 2. Any questions on that first step? Hopefully not too bad. Alright, second thing you want to do is, if you take a look at the next component of the reaction, this one is O2, and I recommend not doing O2 because if you notice, O2 is split between 2 different equations, right? So that means you got to add it up at the end. So a little bit tricky to keep track of that, and it should work out if you guys do it correctly. So we're going to skip O2, and we're going to go to NO instead. So that's a little tip that I want to give you. If you have a component that's in multiple equations, skip that one and go to the one that's just in one of them, because it just makes it easier. Okay, so for NO is in equation 1, and the only problem is that you need to double it. So you're just going to double equation 1. So 2N2 plus 2O2 produces 4NO, and for your delta H, you just need to double negative 180.5. Okay. So that's the next step. Equation 1, and I'll write the equation. This is equation 2. This is equation 1. All right, and then for the last equation, equation 3, the component that we have is H2O, and it looks like we need to triple it to get from 2 to 6. We're going to triple it. That'll give you 6H2 plus 3O2 produces 6H2O. So delta H, you're just going to multiply it by 3. All right, so if we combine everything together, let's take a look at what we got on the left and the right side. First thing you should notice are the 6 H2s. So the 6 H2s will cancel each other out. You also have 2 N2s, which cancel each other out. And then from here, just combine everything. So you got 4 NH3 right here, plus 2 and 3 O2s. That equals to 5. So eventually it does work out to 5O2. You got 4 NO plus 6H2O, and that's how you can confirm you did it correctly. And then if you do your delta H, you should get somewhere around negative 1628 kilojoules per mole. All right, so enthalpies of formation is a little bit different than what we've been talking about. We've been talking about regular enthalpy. All right, so let's talk about enthalpies of formation. So enthalpy of formation is a little bit different than regular enthalpy. So first, you'll notice the symbol looks a little bit different. So delta H, degrees, and then lowercase f. Okay, so enthalpy of formation. A little bit of a different symbol, but let's talk about what it means because it has a very specific definition. Okay, enthalpy of formation is basically the delta H when you are making 1 mole of a substance. So it's the equation, you're gonna have 1 mole of your product, and it's made from the most stable form of its constituent elements. Okay, so you're trying to make 1 mole of a chemical from its elemental forms. We talked about it before, from their elemental forms. Okay, so it's a very specific type of reaction. Again, you have to have 1 mole of whatever you're looking at on the product side, and then you need the elemental form of what it's made out of on the reactant side. Okay? So we're going to look at a couple examples, but again, this is a very specific definition and a very specific type of reaction. There will be problems where they try to trick you. Maybe they might put like 2 moles on the product side. That would not be enthalpy of formation. It has to be 1 mole, and it has to be elemental forms, the most basic form of its constituent element. So let's take a look at CO2. Okay, so enthalpy of formation of CO2. You're trying to make 1 mole of CO2. Okay, so if you notice, there's 1 mole of CO2 right here. CO2 is made out of carbon, and it is made out of oxygen. Okay, the elemental form of carbon is something called graphite. So this one you actually need to remember because they'll try to trip you up. The elemental form of carbon is solid, but specifically graphite. There are other solid carbons. So for example, the one that they throw out a lot is solid carbon, but diamond. So diamonds are technically solid carbon. It's also solid, but it's not the elemental form. Okay, so this would not be the elemental form of carbon. It has to be solid graphite. Carbon dioxide is also made of oxygen, and the elemental form of oxygen is O2. It's those diatomic gases that we've been talking about. Okay, and that's what the equation for enthalpy of formation is. It's 1 mole of the product and the elemental forms of what it's made out of. And then it gives you the delta H of formation. Okay, so if we take a look at our next example is for liquid water. Okay, water is H2O. So we got 1 mole of water. Okay, it's made out of hydrogen and oxygen. Both of those are diatomic gases. So the elemental forms are H2 and O2. Okay, however, because if you look at 1 mole of water, there's only 1 oxygen, right? So in order to get the enthalpy of formation, to have only 1 mole of water, you have to half the O2. Okay, so for enthalpy of formation, you can have fractions for your coefficients. Okay? Just keep that in mind. You need to balance it, but you need to keep only 1 mole on the right side. So there are times you will have to use fractions for your coefficients. Okay, because elemental form of oxygen is O2. You only need half of that. You only need 1 oxygen, and so we put a half in front of O2. Okay, so just a heads up about that. You will have fractions for your coefficients for enthalpy of formation. All right, last thing I want to mention before we move on. If you are trying to find the enthalpy of formation of a compound that's already the elemental form. So for example, oxygen, O2 gas is the elemental form of oxygen. The enthalpy of formation of an elemental form is going to be 0. Okay, because it's just the same thing. Same molecule on the left and the right side. Okay, so those are the 2 things that are kind of new with enthalpy of formation. You can have fraction coefficients. Okay, so if you want to make a note, you can have fraction coefficients. Okay, and then the delta H for an elemental form is going to be 0. And if you take a look at Appendix C in your textbook, you should be able to see a huge table with all the enthalpy of formation for different compounds. You do not need to memorize any of them. The only thing you do need to memorize is the elemental forms, but it's like the stuff we talked about, oxidation reduction, the diatomic gases, and things like that, the solids and whatnot. All right, guys, so let's go over these equations. Let's see which ones are enthalpy of formation, and if not, how we can fix them. So let's take a look at A. Okay, the answer for A is yes, this is enthalpy of formation. How do we know that? We have 1 mole of product and elemental form, sodium, solid sodium, and diatomic oxygen gas. Okay, so those are the 2 things we can look at. 1 mole of product and the elemental forms. All right, if we look at B, what about this one? Is this enthalpy of formation? No, it is not. Why not?
2 moles.
It's 2 moles, so this is no. So if we're going to fix it, the first thing we want to do is product side. We need to make this into 1 mole. So we're going to have to divide this equation by 2. Okay, so we got to get this to 1 mole. There's actually one more thing that's wrong with it. What's the other thing that's wrong?
Potassium.
Yeah, Cl, we got to get it to half, but potassium, what's wrong with potassium?
It's not.
It needs to be solid to get elemental form. So K solid plus 1/2 Cl2 gas. Okay, so those are the 3 things that we need to fix up. First thing, you got to get this down to 1. Next, change potassium to solid, and then 1/2 your chlorine gas. All right, and then since you guys got B, I'm sure you guys got C. Is C elemental form?
No.
No, it is not. What's the first thing wrong with it?
It's diamond, not graphite.
Exactly. We got to change diamond to graphite. What else? It needs to be flipped. Yeah, because we need 1 mole of the product. So we're going to flip it. So C, 6 moles of solid but graphite carbon plus 6 moles of H2 gas, and that's okay. 3 moles of O2 gas, and that's okay because they're diatomic, makes 1 mole of glucose. Nice. You guys did get it. Okay, guys, so now we're going to move on to continuation of the enthalpy of formation. Now, we're going to be looking at how to find the enthalpy of a reaction using the enthalpy of formations of different compounds. Remember how I said earlier that in Appendix C of your textbook, there's this chart that tells you the enthalpy of formation of different compounds? Well, using this chart, you can figure out the enthalpy of a reaction. Okay, now, what we're going to do is we're going to learn how to do that, and it's pretty simple. I'll break down what this equation means, and you guys can write it however you want. So, the enthalpy of a reaction, the total enthalpy of a reaction, this sign is a Greek letter, sigma. It just means sum. So basically, all of the enthalpy of formation of your products minus all of the enthalpy of formation of your reactants. That's pretty much what it's saying. Basically, you find all the enthalpy of formation of your products and just subtract the reactants, and that will give you the enthalpy of the entire reaction. Pretty simple. All you have to do is be able to look at a table and just do some basic math, and then you should be fine. We'll go over how to do 22, and I'll have you guys do 23 on your own. But that's what this equation means. Okay, if you don't like the sigma symbol and whatnot, you can just write all of delta H. All right, guys. So if you guys have it up on Canvas, you guys can zoom into this table right here because I know it's a little hard to see on the screen. But we're going to be taking a look at this reaction right here. Anyone know what this reaction is? You guys have seen it before in bio.
Cellular respiration.
Yes, it is cellular respiration. Yes, that's very impressive. Yeah, so plants use oxygen and glucose to make carbon dioxide and water. Okay, so let's take a look at this. So first thing we're going to do is we're going to find the sum of your products and then subtract your reactants. So let's look at our products. Our products are 6 moles of CO2. So our delta H of our reaction is going to equal 6 moles of CO2. So we look for CO2 in our chart, negative 393.5. So 6 times negative 393.5. Okay. Plus 6 moles of liquid water. So we're going to look for liquid water, which is not here, but it should be above if you look up at the example 2 right here. Liquid water is negative 285.8. Oops. So plus 6 moles of water, which is negative 285.8. And so this right here is going to be your products. And I'll color code it just so it's a little bit easier to see. Okay, and then we're going to do minus the sum of the reactants. Do you guys think you could try the reactant side on your own? I'll take your silence as yes. Okay, so try reactants and see if you can get the final answer. So for water, hopefully you guys remembered what's the rate of formation for elemental forms? Or not water, sorry, O2. What's the rate of formation for, 0. If you see an elemental form, that is always going to be 0. Okay, also you could have scrolled up and then you would have seen it. All right, so again, products minus reactants, and that'll give you your final answer, and you should get about negative 2802.8. Oops. And then make sure you gotta label it kilojoules. Alright, and that's pretty much it. That's how you do delta H formation. That's how you can use the chart to find the enthalpy of the reaction. Okay, so hopefully the first part wasn't too bad. You just needed to use the table. A lot of these we actually used already, so you can just find the enthalpy of formation, the rate of formation for these, and I put the numbers there for you. And then we do the same thing, products minus reactants, and that should give you this value right here. However, the key is that if you look at the reaction, how many ethanols are there? So we're looking for 2, but how many are in the reaction? 1. So what do we need to do at the very end? Yeah, we gotta multiply by 2 because the reaction has only 1 mole of ethanol. We're looking for the combustion of 2 moles of ethanol. So we gotta double that, and that should give you negative 2,733.4, around there. Okay, so that's the key on that one. You just needed to double it at the very end because the reaction only has 1 mole, but it's asking us for 2 moles. Okay.